That's why they're coming in for help. Yeah, I thought, well, if that person did it, then there's more people doing it. That's what we're going to test, a personal test.
Well, as soon as you do, somebody's
Oh, I think so, yeah. Explaining it a little bit.
Managers and what you're not going to make. Oh, seriously.
Thank you for joining me. So today I'm going to be talking about God, physics, and our universe. So a bit about me. My background is in astrophysics, and I study an area called quantum gravity. And I can assure you, nothing in this talk will be about quantum gravity. But we are going to talk a bit about science, a bit about theology, a bit about philosophy, and how they all sort of fit together. So why is this important here? Well, we're talking about science and technology and theology, and science is the foundation for most of our technology today. Right? We're able to make transistors in our computers that are literally the width of a couple atoms. And even a decade ago, that seemed rather impossible. We've also been able to leave our planet, right? And we've been able to do all the calculations to be able to put a probe exactly around another planet, billions of kilometers away. So this has all been enabled by science. And why has science enabled technology the way it has? Well, to begin, we need to talk about what is science. Now, science can mean a lot of different things. And so I'm not going to claim to have the definition, but I do want to talk about what science generally has in very broad terms. So one is it's a methodology, right? It is a way of approaching the world. It's a way of modeling what we see around us. It's a way of using those models to predict things in the future and also to make extrapolations in the past. And it's also a method for verifying our understanding. People will also talk about science as if it's a body of knowledge, right? They'll talk about it as if it's some set of truths. And so, in my opinion, that knowledge is a combination of our observations and predictions, especially the ones that have been successful, as well as the models and the interpretations that enabled us to make sense of those observations. So, what is required for science to do that? And this is sort of where we venture into philosophy. So we require a universe with certain properties for science to work the way it does. One is our universe has to be accessible, right? We have to be able to know things about our universe to be able to describe them. Seems fairly basic, but when you really drill into sort of the foundations of knowledge and the foundations of knowing, this can get quite complex. We also require a universe that's consistent, right? If we describe something today, it has to work tomorrow. Otherwise, everything we're doing with technology and science isn't reliable, right? We have to relearn our science every day. And the other aspect is it has to be intelligible, right? We have to be able to make sense of it. And that's something very unique to humans, right? And the fact that humans are able to make sense of our world was not a guarantee. And so this is something we can point to that is almost borderline miraculous. Right? The success of science is rather profound. And combined, this allows us to make predictions, right? And this is where the power of science really becomes evident, right? I can design a microchip and have it work as expected because I have a good understanding of, electrical engineering, of quantum physics, right? How things work on small scales. And so because of its success, science has a lot of trust. And so we want to sort of dive into that because people will look at science and they will look at how much they trust it, and then they will do more with science than maybe is warranted. So science can come into conflict with theism and other worldviews. when people start making claims about science. So these are not claims from science, right? They're claims about science. So the first is that science is capable of explaining everything that exists. And this leads to something called scientism, right? You can almost think of this as a complete and total faith in science. Another claim is that science is capable of verifying all claims that have meaning. But science isn't something that really produces meaning. We'll discuss that a little bit. But this results in an area called verificationism, right? The only things worth believing are the things that can be verified. And together, these are both different forms of something called logical positivism. And this is an idea that doesn't really work out. And that's largely because there's a metaphysical assumption in between, right? And like I was saying before, these are based off of claims about science, right? It's a metaphysical framework people are putting around science and then presenting it like it is science. So what is that metaphysical assumption? Well, everything that exists meets our criteria, right? How we defined science before. It's accessible, intelligible, and it's consistent, right? That's an assumption. There could be things in our reality that don't meet those criteria, and science might not know about them. And we assume that the only meaningful claims are empirical claims, which is also somewhat problematic. So with that first assumption, if something is not accessible, intelligible, or consistent, like I said before, then it can't be considered by scientific methods, right? And so if we can't use science to verify it, then how can we say that it's good or bad, right or wrong? It simply doesn't apply, right? It is an error in category. With the second assumption, if a claim is not empirical, then how would we test it using empirical means, right? You wouldn't go to an art museum and point to a painting and say, please measure the beauty of this painting with a meter stick. It's the wrong tool for the job. So we can't use an empirical test to evaluate something that is trying to derive meaning. And more importantly, the second assumption is not an empirical claim, right? It is a claim about meaning, and it is a claim about all claims. That's not a part of reality. It's not observable. It's not tangible. And if there's something that doesn't fall into this, empirical methods wouldn't know about it. So this leads us to ultimately a problem with putting too much trust in verification, right? And ultimately, when it comes to verification, there is some element of faith. So when we're evaluating our beliefs and we're trying to justify them, right, all the way down to the foundations, we end up with three unsatisfactory options. So the first is a reductive argument, right? And this is fairly common in science. But instead of trying to prove this thing, you reduce it into something more fundamental, and then you try and prove that. But of course, this strategy only works so long as you can keep reducing. And eventually you're going to hit a belief that can't be reduced any further. You're going to hit something so fundamental that there's simply nothing to reduce. The second is a circular argument, right? So when you hit that limit where you hit something fundamental that can't be reduced, usually you're in a place where you need to use the thing to prove itself. And if you're trying to ground something on reason, a circular argument is a fallacy, right? And so that's very unsatisfactory. And then the third is the axiomatic argument, right? You simply take it to be true. You don't try and justify it. And this can be somewhat problematic because if you're just taking things to be true, not necessarily blindly, maybe it's from experience, or maybe it's from intuition or something else, but not justified, it starts looking a lot like how you might define faith, right? And so the axiomatic argument starts looking like faith of a kind. And many people do not like that because potentially it would leave their entire worldview, right? How you build up knowledge, how you verify it, on a foundation of faith. So, shifting gears slightly, what can science predict, right? Well, science works off of this idea based around determinism, which is the thought that if you know enough about now, you can make a good prediction about the future, or extrapolate what happened in the past. And the idea with a hard determinism, right, or a strict determinism, is that if you know everything about now, you can make perfect predictions about the future. And because science is naturally doing this on a methodology side of things, Science is often linked to this view, but it has its limits, and ultimately that's not really a problem for science. But we can ask, does hard determinism make sense? And so I'm going to throw out a bit of a thought experiment here, small argument, and just to illustrate what happens when you start with these assumptions and work them through to their natural conclusion. So if the universe is fundamentally deterministic, right? So it has the qualities that allow us to know everything about a certain moment in time and make perfect predictions about the future, right? So we're going to assume this is the case. Then premise 2, we assume that all human faculties are also a product of determinism, right? Because we're a part of this universe. Our brains are made up of content of this universe. And so if the universe is fully deterministic, then our brains must be fully deterministic. And then everything we're capable of doing is also determined by our brains. Yet, we all know that humans are capable of being both rational and irrational, right? And we've all probably had those moments where emotion has won out over reason, over good judgment. And this is a part of our experience. And so the problem is that if we're just products of determinism, then we can't choose to follow the rational conclusion. Right? If we happen to, that's just what we were determined to do, right? So, in effect, humans are not capable of reaching rational conclusions. It's just sort of happen chance if we do on this view. Right? Now, it turns out our universe is not fundamentally deterministic. Right? That's the lesson of quantum mechanics. I'm not actually going to teach quantum mechanics, so. But the idea is that there are random elements to reality, and that forms the basis of our physical universe. And so premise 1 goes out the window. Premise 2 also makes assumptions about what it means to be conscious, what it means to be an agent. And that's very much an open question. And I'm not really qualified to even attempt to answer the mind-body problem, if you're familiar with that. But the only point here is that it is very much in question. And if we have a certain degree of freedom, right? So if we're not these deterministic machines, but there is some aspect of agency to us, then we can simply attribute those irrational moments to that agency, right? It's a choice. It doesn't invalidate our reason. It's just that in the moment, the individual didn't choose to follow it. Now, I'm avoiding terms like free will because that's a fairly large can of worms I don't want to open today. But merely to point out that if it's not deterministic, right? So whatever the alternative is, that's a different thing we can discuss later. But ultimately, I just want to point out that the determinist point is doesn't follow there. So what this means is that for science to be effective, it requires agents, right? It requires people committed to doing the science, following the scientific method, following it ethically, right? Reporting true results, and so on. So there are some limitations of science, just in review, but basically what we should conclude from this is that science is not all-encompassing, right? So scientism doesn't apply. And verificationism has its limits too, right? We can't just assume we can verify everything through empirical means. And so there is a scope on science, and it is not complete. So from here, I'm going to switch gears slightly. So my background is in astrophysics, so I am going to talk a bit about astrophysics. I'm not sure if it'll all make sense. Hopefully it's somewhat entertaining, but I'll enjoy it. So there are a few things when we look at our universe. One is that it seems very specially suited to us, right? And so one of the classic arguments is called a fine-tuning argument. And if you look at, say, the physical constants, right, so things that we've derived in physics, what you find is that if you change their value even slightly, everything breaks. So here we have the gravitational constant, and if you change it by, 1 decimal place, just a little bit, if you make gravity a bit weaker, then you don't have galaxies forming, you don't have planets or stars forming. If you make it a bit stronger, everything starts collapsing into black holes, which isn't great. So it has to be precisely what it is for the universe that we see. There's another one called a fine structure constant, and I won't go into exactly what this is, but it comes out of quantum mechanics, and it's very important. But all is that to say is if we change it even slightly, we don't have atoms, we don't have chemistry, right? Everything breaks down. So on the one hand, we have a universe that seems very finely tuned for us, but if we look out into the cosmos, it's also incredibly hostile, with the exception of where we are. So a couple scientists, so Peter Ward and Donald Brownlee from the University of Washington, proposed this theory. And it is just a theory, it's not conclusive. But it's this idea that if you look at all of the elements that makes Earth's position unique, and all those factors that made life or were beneficial to life, then maybe Earth is actually a bit of a rarity in the universe. Maybe life isn't as common as we would think. So I'm going to go through some of those, but to begin, I wanted to look at this quote from Isaac Newton. The most beautiful system of the sun, planets, and comets could only proceed from the counsel and dominion of an intelligent and powerful being. And if the fixed stars are the centers of the other like systems, these being formed by likewise counsel must be all subject to the dominion of one. Now this is important because it comes from a book translated in English as Mathematical Principles of Natural Philosophy. And if you're not familiar with it, it is the foundation for all modern physics. Right? This is the introduction of calculus for physics. All the mathematics for every STEM field is based on work done in this book. And the author attributes the order in the universe to one being, to a theism. And so keep that in mind as we start looking at some of the factors that makes our place in this universe special. So for the Earth, there are dozens of these different criteria. I'm only going to quickly go over a few. One is we have a large satellite. We have the moon. And that has its benefits. We have a magnetosphere, right, a magnetic field around our planet, which helps deflect radiation. And we have an atmosphere that's well suited to exactly our position. So for satellites, you can see with the moon, it takes a lot of hits for us, right? It picks up a lot of objects spinning around us. And as you might know, asteroids hitting Earth is not a great thing, right? It's usually attributed to extinction events. And so it's very likely the moon has prevented several of those. It also has some other benefits. It introduces tidal forces. And I won't get into all of that because a lot of them can be linked to evolution and things like that, and that's another talk, so we'll keep it here. But if you've ever been to a tidal region, you'll see that it's very full of life because there's an exchange of nutrients between the ocean and the land. And so even in our present state, tidal forces are really important for ecosystems. We also have additional orbital stability by having a large moon, right? Two objects orbiting each other, right, tied together by gravity, is more stable than a single object because there is momentum there that you have to overcome to try and disrupt that system. And so there are some benefits to our orbit. So with magnetic fields, you can see here the white lines are the field lines of our magnetic field, and the color is radiation from our sun. And you can see that it's being deflected. Some of it will follow the field lines down into Earth, and that's how we get the aurora. But the majority of the radiation is bypassed because we have this field. Now, it turns out that magnetic fields are not necessarily common, at least in our solar system. There isn't a lot of data on magnetic fields around planets in other solar systems. Exoplanet discoveries are still happening, and detecting magnetic fields that far out over very small bodies is a difficult task. But we can look at what we see in our solar system as a bit of context. So we have Mercury, which has a very weak field because it's not spinning fast enough, is the theory. And so that's another factor. The planet needs to be spinning fast enough to have sufficient magnetic field. Venus and Mars don't have one, but Mars did in the past, and that's another factor. You don't just need a magnetic field now, you need it for the entire span or duration that life is going to be on the planet. Atmosphere is also really important. So Venus has a very thick atmosphere. And so it has a very cozy 464 degrees Celsius on the surface. I don't recommend vacationing there. It's also under 92 atmospheres of pressure. And for context, air pressure at sea level is 1 atmosphere. The pressure at 1,000 meters down underwater, a kilometer, is about 92 atmospheres. So that's how much pressure is on the surface of Venus. Mars is sort of the opposite. It ends up being rather cold, anywhere from -80 to about +5 or 6. And it only has 0.006 atmospheres of pressure, right? Not enough to breathe. Now this is important because both of these planets are in an area called the habitable zone, right? So it's this red area here, and this is a distance that is just the right range from the sun, right? We get enough radiation that our planet is warm, we have liquid water, but we're not so close that it all boils off and we get irradiated, and we're not so far away that we're just an ice ball. So this is an important place to find your planets. So not all planets are in this zone, and that potentially rules them out for life. It's also not a fixed zone. This will change over the life of the star, right? Stars contract and they expand over their lifetime, and the amount of radiation they put out changes depending on where they are in their fusion process, right? Because they're fusing heavier elements, and eventually they run out of fuel, and so their output changes. And the habitable zone will change in result. And so you don't need to just be in it now, you need to be in it for long enough duration for life to do whatever it needs to do. We're also benefited because we're around a single star, right? Depending on which surveys you look at, most star systems seem to be multi-star systems. And that means there's a lot more dynamics going on. It's not often that you'll find 2 stars that are the same, so they're not aging at the same rate. One might start expanding, the other will start cannibalizing it, pulling material off. And when that happens rapidly, you get something called a nova, right? A massive explosion, and that is not great for life on any nearby planets. So single stars are definitely beneficial, and single stars of a particular type and mass as well. There's also something referred to as a Jovian shield, basically a Jupiter-like object in the outer solar system that picks up small objects. So similar to our moon, it's also acting as sort of a catch-all. And it has dozens of moons, and many of those would have been objects that would have made their way into the inner solar system at some point. Earth also has a stable orbit. It's mostly circular for the most part, slightly elliptical, but overall stable, which is beneficial because, again, you don't want to be venturing in or out of that habitable zone. And then there's this idea called metallicity. Now, astronomers really like to infuriate the chemists, and we call everything heavier than helium a metal. It's very confusing for everyone else, but we stick with it. But the idea is that we use this as a measure for how much other elements are present, right? So if you need life to have a complex chemistry, say water, you need oxygen. And measures of oxygen versus helium are really important to determining which systems might support life, at least life as we understand it. The galaxy also has a habitable zone. So we end up being in it. It's not quite as clean cut as this, but this serves well for illustration purposes. But this exists because certain stars will go supernova at the end of their life. So they have enough mass, they explode, and it's very energetic, far more than a nova. And it's so much so that it can eradicate life in nearby star systems, right? So one figures that supernova will outshine the entirety of the galaxy that they're in. And we've seen this multiple times. They're very energetic events. And so you don't want to be too close to them. But at the same time, heavier elements are made inside stars. And when the stars go supernova, that's how the heavier elements get distributed. And so if you need a certain amount of chemistry to occur, you need to be around some supernova, but not too many. And so in the center of the galaxy, stars are really dense, so you're more likely to be near a neighbor that goes explosive. But if you go too far out, the density has fallen off, and you might not be near a supernova or a remnant of one where you have sufficient elements to have life-bearing chemistry. There's also an area of our local universe called the local group. And so there's only 3 galaxies here, the Milky Way, Andromeda, and Triangulum. And it's overall relatively empty. We're also not threatened by something called an active galactic nuclei. In short, as matter falls into the center of the galaxy, we think there's a supermassive black hole, and some of that matter will get accelerated. They're basically natural particle accelerators, And they shoot out these streams of high energy radiation, and they can go out quite a ways. And so if you're a neighbor and you get hit by one of those, there's a good chance that life in that galaxy will end. We also have no immediate risk of collision because of our neighbors. Everyone in 4.5 billion years will have to worry about Andromeda there, but until then, we're probably okay. So large clusters are pretty common. At the top here, we have the bullet cluster, and this is actually two clusters that have collided, right? Illustrating that usually these things are a lot more energetic. They're also a lot more dense, right? There's a lot more galaxies. So to illustrate sort of what galactic collisions look like, we've got this little simulation here. And the only important point to note is that during this collision process, they sort of start orbiting each other, and then in that, they start throwing off stars into the cosmos, which, if you need to be near other stars for heavier elements, or you want to avoid colliding with other stars and having your planet stripped from your solar system, or potentially two stars merging together into one solar system, you typically want to avoid these. And then just quickly to illustrate what active galactic nuclei look like, so we've got two examples here. But these jet streams go out millions of light years. And if we go back here to the local group, you'll see that the scale is on the order of about 4 million light years. So if we had more neighbors and they were pointed in roughly the right direction, we might not be here. So what does this all mean? Well, the universe is really big. There's about 2 trillion galaxies, or 10 to the 24 stars. And the usual analogy they have for that is if you counted every grain of sand on a beach, and on every beach on Earth, you would still have fewer than there are stars. Now, this is often used to justify that life is inevitable, right? Maybe it is hostile, but ultimately, there's a lot of it. So we only need it to happen maybe a few times, and we'll be fine. So in conclusion for this, we have a universe that is fundamentally fine-tuned for life, and also overly hostile for life, except for our little corner of it, as far as we can tell. Now the question is, what do we do with this? And it's not necessarily a scientific question. So when we do science, often the assumption is that we should remove ourselves from the process. Right? We don't want to assume we're in a special place. We don't want to assume that science is a very human-centric activity. And so this is known as the Copernican principle. But it's also contrasted with the anthropic principle. Ultimately, we are humans doing science, looking at things from a human perspective. And so we can't necessarily remove ourselves from it either. So what do we go with? Well, I'm not really going to answer that today, but only to point out that there are assumptions that we use to frame science. And just like before where we were making claims about science, often when there's conflict between science and something like faith or religion, it's because of the assumptions about science, not the claims coming from science. And because this is an apologetics conference, it wouldn't be a proper presentation without a quote from C.S. Lewis.
Amen.
So men became scientific because they expected law in nature. And they expected law in nature because they believed in a legislator. And so I think this is an important part about how a Christian is going to frame science, right? We expect to see order. We expect to see law. We have the anticipation that mathematics is going to work because there is an order and a reason behind everything. So in summary, science is defined as knowledge and a methodology. It requires certain things from our universe, right? It requires consistency, intelligibility, and accessibility. Science is also grounded on a faith of a kind. Some people don't like calling it that, but there are certain things you're going to have to simply take to be true to get started. Science requires agents to do. We have to be able to choose the science or the scientific or the rational conclusion. And science shows us a universe that is both well-suited to life and also paradoxically hostile to life, except for our little corner of it. Now, this might be a problem for a naturalist, but for the Christian worldview, this is exactly what we would expect, a universe that is well suited to us, right? And it doesn't matter if most of it is hostile, because we only need this part with us to be ideal. So to quote Psalm 19:1, the heavens declare the glory of God, the skies proclaim the work of his hands. And Christians approaching science with this view are already expecting to see that order. We already accept that the universe is going to be this way. And so when it comes to sleeping at night with all of our discoveries, Christians probably do it a lot better. Any questions?
Astrology in February of 28, all the planets were lined up. Yes.
Think so? Yeah, that sounds right. Yeah.
It was almost 304 years ago happened that, right?
Yeah, something like that. Yeah.
When you said the universe is big, do you mean the observable universe or just okay.
Yeah. Well, and that's an interesting point too, because you do have scientists that will make assumptions about things we can't observe, and you have to wonder if that is actually a scientific conclusion, or if it's more of a philosophical or metaphysical, right, conclusion you're trying to draw. Because if you can't observe it, or if you can't infer it's going to be there, maybe it's not worth, guessing that it's there. Yeah. Depending on the context, but yeah. Any other questions?
So, in light of all this information, can we say how old the universe is and how old the Earth would be?
Yeah, throwing me into the deep end. All right. So I'm an old Earth creationist. I'm not expressing the opinions of Apologetics Canada. Yeah, I think recent estimates on the universe is 13.7 odd billion years old. Earth is, I always get it backwards. It's either 4.5 or 5.4. I think it's the first one. Billion years old. Whether or how you want to fit humanity into that picture, I think, is a different question, at least slightly. But I think we look at the universe and we see an old universe. Hopefully that answers the question. Maybe. You're nodding.
I've recently seen something where the person making the presentation, I didn't indicate any faith, but he was saying that the solar system, when you look at computer models of how solar systems develop, the gas giants are not where they are in our solar system. They tend to spread out differently. I don't know but he was saying that the only way we can have life is if they spread out where they were, not spread out by how the computer models say that this is where they should normally spread out. Talking about the inner planets. I don't know if you can comment on that or.
Yeah, so I don't know if I know exactly the research you're pointing to, but it is true that we don't know exactly how, or we can't say that our solar system is a typical solar system. It seems, based off of modeling, to be more unlikely. Especially with gas giants, because normally mass tends to congregate near the star, near the early solar system, like as everything's sort of coalescing towards the star. So having large bodies that are approaching sort of stellar mass levels like Jupiter is very unlikely, especially that far out. Yeah. Not to say that it's maybe rare. I haven't seen any data about that, but it definitely seems less likely than not. But yeah, there's lots of factors I didn't talk about, but there's definitely like solar system formation and other things like that. Hopefully that answers your question.
Well, it's just that this guy particularly, like I said, this guy didn't indicate any faith that he had, but he said, he was making the claim that this is very rare and we don't understand how come our solar system developed in a way so unlike the computer models and yet so positive towards life formation.
Yeah. Well, if you look at, say, the rare earth hypothesis, and again, it's not conclusive, but one of its advocates is actually Richard Dawkins, right? And he thinks that that's fairly viable too. And so if you have people on both sides saying maybe this is a possibility, I think it's at least worth considering, right?
Yeah.
Sure.
Are there any images from the James Webb Telescope that have come out that you yourself as a Christian have been particularly excited about?
Yes, though I can't think of any off the top of my head. Part of it is that the analysis of the images takes a long time. And so as the scientist, I see the pretty image and I'm like, okay, but what does the data say? And so there's a lot of data that I'm still waiting on, at least for the areas I'm interested in. But there are potentially a lot of data coming in from James Webb about, say, Hubble's constant and something called the Hubble's tension, but basically how the universe is expanding, whether that's changing or not. And it potentially allows us to answer some of that problem, but they're still sort of working through the data. And so I think there's a lot of very exciting things there. Yeah. Thanks.
Regarding your faith, did you come to the faith because you're a scientist, or how did you come about it? Was it a result of going into astrophysics? Or?
So I was saved when I was young,
Yeah.
but I would say that when I hit academia, I ran into a lot of sort of opposition to my faith. And so that was probably an area of doubt. And then that's probably when I started pushing into astrophysics because I wanted questions. Because I saw these professors being very atheistic on the podium, and I wanted to ask, are they right? And I couldn't answer those questions. And so that was sort of a drive. And what I found was different than they were, or what they found. And a lot of it comes down to, it's not the science, it's how you frame the science or what you bring to the science.
Do you find that you've got a lot of colleagues that are sort of leaning in that direction, or are you an anomaly?
So astrophysics, from what I remember, is probably one of the few areas in STEM that is rather religious. And I think it has something to do with just looking at grand scales and feeling really small in comparison. There's something very humbling about that. Whereas if you talk to biologists or people working on really small scales, they feel like they can control everything, or at least in principle they might be able to control everything if they just understood more. So it's not really a scientific explanation, but I think there's a human component there. Yeah. Yeah.
In regards to mathematics and physics, and how, I want to know from your perspective with those, in looking at a particular way of doing mathematics or like laws of physics, and you sort of enter into that realm, you know, sort of putting on that lens of how these certain rules operate. How do you go about knowing, like, putting on other types of math, other types of, like, you know, reaching other areas of mathematics or physics that would seemingly make certain traditional elements of physics, or, you know, whatever you currently believe, make it obsolete or change it, right? Do you know what I mean? Where there's like different math that you can sort of enter into and understand something completely differently?
Yeah, I mean, to some extent. So in physics, we're very comfortable with the fact that our models aren't perfect. They're not exact. And so we're always making approximations, right? We're always dropping some of the higher order terms or whatever it might be. And so we know there's something more there, right? And so we're familiar with this idea that our models are not complete. And a lot of what we're doing is trying to find models that are. But often the amount that's missing, sort of in value, is very small these days. So, you know, on a scale sort of way of looking at it, they're not big problems in the sense that we're missing lots, but explaining that small part is exponentially more difficult. So there is this, like you're sort of getting at, the mathematics gets very different, but
Yeah, it gets weird.
It gets weird, very weird.
It's weird.
But yeah, I don't really see it as a problem, more just almost like a next step, right? It's like going to the next chapter in a textbook that introduces a more complex topic. And we're just sort of figuring out what the next chapter is. Yeah.
I'm not entirely sure I have a question. I think I want like your comment on something that I heard recently.
Okay.
So I was listening to Neil deGrasse Tyson, who's professes to be agnostic, and he was speaking about the size of the universe and how oftentimes people use that and they feel very small and they lose faith because they're so small in a universe of 24 trillion galaxies. And he said, well, let's just look in the opposite direction and find out where we are. So he looked at, let's take the smallest thing we know of, which is the Planck length, and the largest thing we know of, which is the diameter of the universe. And where does a 6 foot tall, 200-pound human fit in the middle of that? And he ran some numbers. I don't know if you agree with the numbers, but he said that we were 10 to the 35 times bigger than the Planck length, but 10 to the 25 times smaller than the size of the universe, which makes us 10 billion times closer to the size of the universe. Which to him, it just kind of hit me, and I thought, he said, do you feel important yet? Because everything bigger than you makes you feel small, but everything below you kind of conspires to make you exist, like your cells and your proteins and everything. And I was wondering if you had a comment on that.
Yeah, I'd want to look at his numbers, honestly, but...
I figured that. I said you were there.
Sure, but one of the difficulties is that the idea of length in a modern sort of idea of cosmology is somewhat nebulous, right? So current models are ones that have inflation. So the idea is that space itself is expanding. So if you were God and you had a measuring stick and you measured a bit of space and then you came back to it later, you'd find that your measuring stick had actually changed. And so I'm not sure if he's accounted for those kinds of factors, because when you start looking at sort of raw data and just what you might look at a surface level, you can get very different estimates for the age of the universe. So, and age is very much connected to size, because speed of light is a fixed upper limit, right? And it takes so long for light to get somewhere. And so if that light's changing on the way, it potentially changes our estimates for distance as well. And whether we account for it or not, that's a different factor. There's a whole field called cosmography, which is all about trying to do measurements in cosmos. But not to take away from that, but it's really easy to divide a set unit of length into smaller bits. But you can't make more space as easily. And so I'm not sure the comparison's fair, if that makes sense.
So you're talking about how space itself is expanding. Do scientists, astrophysicists, do they have a theory on what lies beyond that?
Well,
yeah, so it gets a little complicated because there isn't really a boundary in the traditional sense.
Okay.
Right? It's more like, if you think of the surface of like a sphere, like a ball, and we're all on it, you can draw dots on it, but then you start pumping up the ball and it starts expanding, right? You don't have an edge. You're just making the distance between the points bigger. And so when you look at space in those kinds of ways, in sort of these higher geometries, it's difficult to conceptualize. And that's not to say that there isn't something to your question there. It's just that the answer is not going to line up well. And you could probably give a whole talk on exactly what that means. I also should point out that inflationary theory is sort of a fix to a problem. And it's a problem that cosmologists wish we didn't have in the first place. So it might not be the answer. It's just sort of the stopgap. Sort of, we threw some tape on it on the model to make it work. So, yeah.
What's the biggest pushback to the fine-tuning argument?
Well, that's a very good question. I don't know if there's so much of a pushback. I'd say the most popular opinion is that they're just brute facts, right? That that's the way they are and they can't be any other way. And if we can't prove that they can be different, then it's not a question that we should be asking. I don't think that's necessarily helpful, because in every other area of physics, changing the parameters and figuring out what happens and seeing what what it describes and whether it makes sense or not, it's just commonplace. So why wouldn't we do that for cosmology too? And so I think it's a valid question, but yeah, I think there isn't really a good pushback. It's usually some kind of assumption for why it doesn't actually matter. Sure.
What does, or who is God to an astrophysicist who believes in him? What does he look like, his characteristics?
So I think it depends on which hat I'm wearing. So if I'm just talking about a theist who's an astrophysicist and not looking at anything else, right, not looking at Christian belief, then I'd say C.S. Lewis's description of a great legislator, right, somebody who laid down law, is probably going to fit most, right, that there is an order to the universe, and that's why. But with a Christian perspective, there's more personal elements, but I don't think that's coming from the science or the astrophysics necessarily, other than maybe how I'm framing things with my own personal assumptions. I think time for one more question, so.
Given how small life is just on Earth, why is the universe so big? If there's stars out there that we will never see the light of, why would they exist, given where we are?
That is a very profound question, and I'm sure God would be the one to ask. My opinion on it is that the heavens have always been a source and a demonstration of majesty and of law in the universe. And everyone can look up at the cosmos and see the stars and see the motion of the planets and learn something. And so I think on a personal level, they're a demonstration. On a more maybe metaphysical level, it might be a necessity, right? To have this small part of the universe as it is, you might need the rest of it to support it. There we go. We're over. Okay, so we'll end there. Thank you, everybody.
So we have a 10-minute break. It was 15, but we're down to 10. 5 extra minutes of astrophysics. And then the main worship session.